Okay, the first video for chapter 10 here, we're going to look at 10.1, 10.2, and 10.3, and these are all about gases. And we did all of this stuff last year, so that's why we're doing kind of three sections in one here. So the first thing is some characteristics of gases, and so let's think back to last year and even a few years ago when we look at characteristics of gases, and remember that gases take the shape of their entire container. Okay, another characteristic of a gas is that gases are very compressible because the particles are really spread out and they occupy a small portion of the actual volume of the container. So that means that I can take the gas and I can, since the particles are so far apart, I can compress them very close together if I have to. Last characteristic is that gases are always homogeneous mixtures with other gases. All right, on to 10.2, which is pressure. Okay, standard atmospheric pressure is required to support 760 millimeters of mercury in a column, which is why 1 atmosphere is 760 millimeters of mercury. Okay, which is the same thing as 760 torrs, which is the same thing as 101.325 kilopascals and 1.01325 times 10 to the 5th pascals. So those are the different pressure units we're going to look at here. So let's convert between the two, or three. Okay, if I've got 0.357 ATM, we're going to convert that to torrs. So you can do a proportion, or you can just think about multiplying or dividing. I'm going to do a proportion that's 0.357 ATM for some number of torrs. And I know that in 1 ATM, there are 760 torrs. And so you end up cross multiplying and dividing, which is 0.357 times 760 equals to 1 times x. So just x. So we end up with 0.357 times 760, and we get 271 torrs. So you can do the ratio if you would like, or you can just think about whether you're multiplying or dividing. All right, so if you look at the next one, we've got 147.2 kilopascals, and I want to know how many torrs that is. Well, in my proportion then, you're going to end up with kilopascals and torrs. Well, 101.325 kilopascals is the same thing as 760 torrs. They're one and the same. You don't always have to have a 1 there. So we're cross multiplying and dividing. 147.2 times 760 is going to be equal to 101.325 times x. So you end up dividing by the 101. And we should get 1,104 torrs. Okay, the next question is a little bit different. It says, on a certain day, the barometer in a laboratory indicates that the atmospheric pressure is 764.7 torrs. A sample of gas is placed in the vessel attached to an open-end mercury manometer. Remember, manometers are just things that measure samples of gases. Okay? A meter stick is used to measure the height of the mercury above the bottom of the manometer. The level of mercury in an open-end arm of the manometer has a measured height of 136.4 millimeters. And the arm that is in contact with the gas has a height of 103.8 millimeters. And we know what is the pressure of the gas. Okay, well, if we look at our picture, because that's going to make our life a little bit easier. Okay, what you've got, it says that we have an atmospheric pressure for the day, okay, of 764.7 millimeters of mercury. And then they give you some heights. Okay, well, since this is an open-end manometer, okay, this whole thing is a manometer. It's an open end because the top portion here is open. So that means the atmospheric pressure is the thing pushing down there, pressure of the atmosphere. All right, and that 764.7 millimeters is pushing down here. Well, I want to know then, what's the pressure of the gas in the purple here? Okay, well, if we look at the heights, notice how this gas here is pushing down on this end, and the atmospheric pressure is pushing down on that end. So which one is winning? Well, this one is pushing down more because the other end is going up. So that means that this pressure of the gas in the manometer is greater than the pressure of the atmosphere, because that's the one winning. It's pushing down more than the atmosphere is pushing down. Okay? So now we look at our heights. Well, it tells me that my height on the arm is in contact with the gas, which is this in the green right here. Okay, that is 103.8 millimeters. And they say the manometer, okay, open end height, which is going to be in the red, is 136.4 millimeters. Well, then the difference, okay, is what I want to add to my atmospheric pressure, because the pressure in the manometer is greater. So we're going to take 764.7 millimeters of mercury. Okay, we're going to add that to the difference of the two heights. And I can just add them straight across here because these are all millimeters. So I get 797.3 millimeters of mercury, which makes sense because this pressure here should be bigger. Now it wants to know what is the pressure in atmospheres and kilopascals. Well, to convert to atmospheres, you simply just divide by 760. There's going to be 1.05. And then you take 797.3 millimeters of mercury. I want to go to kilopascals. Okay, it's actually probably easier to go through atmospheres because I'm going to end up dividing by 760 and then multiplying by 101.325. You're going to get 106.3 kilopascals. Again, if you don't like it like this, then just set up the ratio. Okay, but this is an open-end manometer. Now, if you have a closed-end manometer, okay, with no atmospheric pressure getting in, this end is shut off, then that means whatever the difference in the heights of these arms is, that is the pressure of my gas. Okay, so if it's a closed end, I don't care what the atmospheric pressure is because it's not doing any pushing. If it's an open end, then I have to take that into consideration because that is also pushing down on those levels of mercury. All right, the last thing here we're looking at is the gas laws. We did these last year. Okay, there are several laws that relate to properties of gases. We've got temperature, which is T, pressure, P, volume, V, and number of moles of gas, which is N. And the first one we're going to look at is called Boyles Law. We did not give names to these last year. Okay, but we have pressure and volume, which is Boyles Law. Okay, if we've got to remember the relationship between pressure and volume. Okay, as my pressure, we'll do volume actually. As my volume goes down, particles get closer together, which means they're going to collide more often, which means my pressure goes up. Okay, so let's remember back to last year, we did these little like before-after deals. Okay, it says sulfur dioxide is a gas that plays a central role in the formation of acid rain. It's found in the exhaust of automobiles and power plants. It says consider a 1.5 liter sample of gaseous SO2 at a pressure of 5.6 times 10 to the third pascals. If the pressure is changed to 1.5 times 10 to the 6 pascals at a constant temperature, what's the new volume? So the only two things I'm looking at here are pressure and volume. Remember we did these charts last year. We've got the initial and then I've got my final. Okay, initially we've got 5,600 pascals. Finally, I have 1.5 million. Okay, my volume starts out as 1.5 liters, and I want to know what is my final volume. Remember, since my pressure is going up, that means my volume needs to go down. So I need to multiply my numbers to make them get smaller, which means the smaller one needs to go on top and the bigger one on the bottom. Because I'm going to give me an answer of 0.0057 liters. Okay, so you take whatever you're trying to fix or figure out goes first, and then you multiply by the ratio, and whether you want to make the number bigger or smaller, whether you put the number that's bigger or smaller on top. So that's the first gas law. The second gas law is called Charles's Law, and this is where we look at volume and temperature. Okay. If I increase my temperature, I heat up my molecules. The molecules are going to move a lot faster, collide more, which means my pressure goes way up. I don't want my pressure to go up. So in order to relieve that pressure that's going up, my volume needs to get bigger. Volume and temperature are directly related. Remember when we talk about volume, okay, it doesn't matter what my unit is for these, but when I talk about temperature, they have to be in Kelvin. Okay. Sample of gas at 15 degrees Celsius and 1 atmosphere has a volume of 2.58 liters. What volume will this gas occupy at 38 degrees Celsius and 1 atmosphere? So again, set up your table, volume, temperature, what you have initially, what you have finally. Initially I have a volume of 2.58 liters. I don't know what my final is. Initially I have a temperature of 15 degrees Celsius and I end up at 38 degrees Celsius, but these have to be in Kelvin. So to go from degrees Celsius to Kelvin, remember you add 273. So that's going to be 288 and 311. Okay, my temperature went up, which means my volume needs to go up. So I multiply with my ratio there to make my number bigger. So I put the 311 on top, the 288 on the bottom, and we get 2.79 liters. Okay, the last law here is the quantity-volume relationship, which is Avogadro's law, which is between amount and volume. All right, if my amount goes way up, I have more particles in there, they're going to collide more, take up more space here, because now I have to relieve all that pressure that I am increasing because of all the collisions that I'm making. So amount and volume are directly related as well. And we do the same thing we did before. I'm going to have amount and volume as my two things. I'm going to look at where we are initially, where we are finally, and then how it changes. So suppose I have a 12.2 liter sample containing half a mole of oxygen gas at a pressure of 1 atmosphere, a temperature of 25 degrees Celsius. If all of this O2 is converted to ozone and the same temperature and pressure, what would the volume of the ozone be? Now you've got a problem here. If all of that was converted to ozone. So now I'm no longer in O2, I'm in O3. So you gotta have a little bit of an equation with it. Okay, so I'm going from O2 to O3. Gotta balance it. Which means a little bit of stoichiometry here. If you have half a mole of O2, how many moles of O3 are you gonna have? Remember back to last year? Okay, you can do a ratio, or you can think, all right, my number here should get smaller. How much smaller? 2/3, because it's 3 to 2. So it's 1/2 times 2/3, which is about 1/3 of a mole. So my final mole number is 0.33. Now what I gotta do is multiply to make my number either bigger or smaller. And my amount went down, which means that my volume needs to go down. So I can take 12.2 times, put the 0.33 on top, the 0.5 on the bottom, multiply and then divide, and we get 8.1 liters. Last one, we're going to put them all together, and then you can do one by yourself. Okay? So if I relate all of these ideal gas equations and gas laws together, I'll put everything together. Okay, I have a sample of diborane gas, a substance that bursts into flames when exposed to air, has a pressure of that, temperature of that, and a volume of that. My conditions are changed to a new temperature and a new pressure. What's my new volume? So now I've got three things going on. I've got pressure, volume, and temperature. Okay, so just write them all down initially and finally. Initially, my pressure is 345 torrs. Finally, my pressure is 468 torrs. Initially, my volume is 3.48. Finally, I don't know. My temperature is initially -15, and my final is 36. But remember, these have got to be in Kelvin. So you add 273, 258, and 309. So now I've got three things changing. So you got to be careful as to how you figure out whether it's bigger or smaller and up or down. So what I do is you take one item that you know how it changed and compare it to what you're looking for. So my pressure went up, which means according to my pressure, my volume should go down. Then you look at the other one and say, okay, well my temperature went up, so according to my temperature, my volume should go up. So they're kind of fighting with one another. The pressure wants to make the volume go down, the temperature wants to make the volume go up. So you're going to end up somewhere kind of in the middle and see whoever wins the fight. So you look at it one at a time. Start out with the 3.48, which is my liters. Okay, according to pressure, here in the red, my volume needs to go down. So I need to put my smaller pressure on top and my bigger one on the bottom. Now, according to my temperature, my volume should go up. So my temperature numbers, the bigger one should be on top and the smaller one on the bottom. Just multiply straight across, divide by the bottom, and we get 3.07 liters. Try the last problem by yourself. Okay, this last one here, you should get 8 liters because, again, they're kind of fighting with one another. Pressure and temperature, one trying to make it go up, one trying to make it go down. So you should have your numbers accordingly there.